Thank you for joining this lesson. We're going to discuss current electricity. It's good for you to know that you can reach out for consultation through 0704 153 366. Through the same line, you can also inquire about our online classes. Number 13, we're told that the graph below shows the variation of potential difference V across the terminals of a cell and the current drawn from the cell. Therefore, we got a potential difference, that is voltage in volts, voltage B in volts. Then we have current I in amperes as shown. That is the relationship. That is the graph. Now we are told to use the graph to determine the electromotive force, that is EMF E of the cell, and also to determine the internal resistance of the cell, given that E equals to VIR. So what we're supposed to know that the electromotive force, which is E, that is the total voltage in a cell before any current is drawn from it. But after it has been drawn from it, due to internal resistance, there is what we call lost voltage. So this EMF is usually split into terminal voltage V plus the lost voltage small letter v. We usually say that this is due to the external resistance, while the lost voltage is due to internal resistance. Therefore, E is equivalent to, because V according to Ohm's law, V is given by IR, then this is going to be current times R plus the same current times small r, which is internal resistance. So now we can agree that in case we write the equation in this way, such that we begin with the terminal voltage which has been plotted, V equals to, then the other side we begin with IR. IR will be negative. Then we will add E. So for us to begin with V, which is IR, we have to take IR negative to the other side where it becomes subtracted, then plus E. Now we are saying we want to plot this one on the y-axis and current on the x-axis. Current on the x-axis. That means the coefficient of current, which is IR, will be given by the slope. Therefore, the slope is going to give us negative R, because negative R is the coefficient of current, and current is the one on the x-axis. According to the equation of a straight line interpretation, then this one has been plotted on the y-axis. We will say that the constant here now, C, is given by what we call vertical intercept, or rather the y-axis intercept. Therefore, the value of E will be given by the vertical intercept, or rather the y-intercept of that graph. The graph is just hanging on the Cartesian plane. It means the first thing to do is to extrapolate it so that it cuts the x-axis at a point, the y-axis at a point. So when I produce my line, yes, I find myself now cutting the vertical axis at a point. We have to interpret the scale very well. Remember, we have only 0.2 units for 10 divisions. So in 10 small squares, we are having 0.2 units. These are volts. What about within one small square? This is going to be 0.2 times 1 over 10. So we're going to have 0.02 volts for every small division. Therefore, from 1.4, we are having 1, 2, 3, 4, 5, 6 divisions. So 6 divisions, each having 0.02, we're going to get 0.02 0.12 volts. 0.12. Yeah, 0.12. Therefore, from 1.4 we had 0.12, and that becomes the terminal voltage. So the value is, when we take 1.4 plus 0.12, we're going to get 1.52 volts. So that is the terminal, that is the electromotive force, the EMF of the cell, which is gotten by the vertical intercept in such a graph. So the next thing now is to find the slope, which will eventually give us the negative value of internal resistance. Therefore, the slope is gotten by change in y out of change in x. For us to arrive at the slope, we just need two intercepts, two coordinates. Yeah, actually I can prefer the coordinates lying here. The coordinates lying here for the slope. Therefore, change in y, I can move from 0, change in y from 1.52, 1.52 up to 1.4. Then I divide by change in x, all the way from this point to this point. This is from 0.2 to 0. 0.2 to 0. Therefore, the difference here is going to be 0.12. So I will divide it with 0.2. This is going to give us, when I take 0.12, I divide with 0.2. This is going to give us 0.6. 0.6. But why do I feel that we are making a mistake? Because according to the nature of this line, the gradient is supposed to be negative. Naturally, it's supposed to be negative. So I'm picking coordinates like 0, 1.52, and another coordinate, which is here, as 0. This is on the same line. So 0.2 and 1.4. So when I take 1.52 minus 1.4, I should take 0 minus 0.2. Therefore, this is supposed to be the other way around. That is supposed to be the other way around. So to correct that, 1.52 minus 1.4, that is the change in y-axis, divide by 0 minus 0.2. Therefore, instead of 0.6, now I'm having negative 0.6. Therefore, if this is my slope, then I just supposed to come here and say, because the slope gives us negative r, then negative 0.6 gives us negative r. That means our internal resistance is 0.6. 0.6. We can very fast go through another part here in section 2. Yeah, we are told a system of resistors connected to 100 volts supply as shown. So this is 100 volts supply. We have 3, 30 and 20 resistors. Determine the effective resistance in the circuit. Effective resistance, we're supposed to know that when resistors are in parallel and they are only 2. So for the 2 parallel, we need to get their product, divide by their sum. This will be 600 out of 50. This gives us exactly 12 ohms. So we have reduced 20 and 30 into a 12 ohm resistor because that is the equivalence. Now it's like we are having 3 ohms and 12 ohms but in series. And resistors in series, effective resistance is given by the sum of the individual resistors. So now we take 12 and 3 to give us 15 ohms to give us 15 ohms. That is the effective resistance in the circuit. Determine or define capacitance. Capacitance is the ability of a capacitor to store charge. To store charge. The ability of a capacitor to store charge. Then we are told that in an experiment or in an electrical circuit, a 2 microfarad and a 4 microfarad capacitors are to be used. Which arrangement is to be used to give minimum capacitance? Justify your answer. So told to justify your answer, it means you prove. So if you arrange them in series, it will be 2 microfarads and 4 microfarads. When you arrange them in series, it's going to be that way. But in parallel, we're going to have them here. Yes, 4 microfarads and 2 microfarad capacitor there. What you should note about capacitors, it is that when capacitors are in series, for us to get their sum, we need their product. This is when in series, yeah? 2 by 4 out of 2 plus 4. So for the series arrangement, we're going to have 8 over 6. And this is 1.33 microfarads. When they are in parallel, for us to get effective capacitance, we add them, 2 and 4. This gives us 6 microfarads. Therefore, the arrangement that gives us minimum capacitance is the series arrangement. Therefore, series arrangement will give the minimum capacitance, and it's shown through a calculation that when in series, that is how we get the sum or the effective capacitance. But in parallel, where there is addition, we are getting a very big capacitance. State 2 factors that affect capacitance. Of course, I believe this is capacitance of a parallel plate capacitor, and the factors are 3. 1, we have the distance of separation, small letter d. Distance of separation. 2, we have an area of overlap. Capital A. The other one is the type of the material used, the dielectric material between the 2 plates. The dielectric material between the 2 plates.